If you follow astronomy, you've probably seen that we have discovered several Earth-sized exoplanets within the so-called habitable zone of red dwarf stars, where liquid water can theoretically exist. Red dwarfs also make up most of the stars in our galaxy, and they are the only type of main sequence star that will exist trillions of years from now once galaxies run out of hydrogen fuel and star formation ceases. Many YouTube videos portray these stars as completely hostile to life, but as always, the truth is a bit more complicated. So the two key questions here are, number one, can we harness the power of red dwarf stars in the distant future? And number two, can life as we know it exist around red dwarf stars today? So some of the answers here are a bit depressing, while others are more hopeful. But with that being said, let's just get right into things. So the main way that we classify stars is based on their mass, and that leads to the temperature of the star. Okay, and red dwarfs are in the M category, so they're around 2100 to 3400 degrees Celsius, and they make up around 75% of the stars in our galaxy. So as you can see in the chart there, most of these red dwarf stars will not live to over 1 trillion years. Only the red dwarfs with around 0.15 solar masses or less, which is probably around less than 20% of red dwarfs, will be surviving for that long. And most of the red dwarfs will be between 0.2 and 0.4 solar masses. Now, as you can see on the right there, within around 12 light years of our sun, there's about 10 of these red dwarfs. So you can see how abundant they are in our galaxy. Now, going into some of the differences between stars, you can see here that our sun is 5,800 degrees Kelvin. And so this means that most of the radiation is going to fall within the visible and near infrared. When it comes to a star like Proxima b, for example, which is the closest star to our solar system, most of the light is going to be shifted into the infrared spectrum. Now, as you go even cooler, even more of the light will be in the infrared and even less will fall into the visible. So TRAPPIST-1, which is around 2500 Kelvin and is actually one of the coolest red dwarfs, almost all of the radiation is going to fall into the infrared. Now, if we define the habitable zone as the region where liquid water can exist given an atmosphere, it's actually going to be slightly broader relatively in a red dwarf because water actually absorbs infrared radiation much better. However, this zone in absolute terms is going to be much smaller because the star puts out much less luminosity. Okay, now when we show it to scale, you can see how much smaller it is. And you can see how the ratios are pretty similar actually when you compare it to the sun. So for the sun, so much of the radiation is in the visible that photosynthesis can happen even further out from where the liquid water zone is. Okay, and it even extends near to where the frost belt is in the solar system. For a red dwarf, since most of the radiation will not be in the visible, you're actually only going to be able to have photosynthesis about halfway through the so-called habitable zone where liquid water will be available, given an atmosphere. Now, there's this question of if other forms of life can have photosynthesis using infrared radiation, but as you can see on Earth, there's very few organisms that can use infrared, and in fact, only a few of them can only use the near infrared. When it comes to the mid-wave infrared and the long-wave infrared, this is basically impossible, and it's basically a higher entropy form of radiation. Now, when it comes to the robo-habitable zone, which is something I've talked about in my other videos, which is basically the area where you can efficiently produce solar power and continually increase your solar power exponentially, this is going to be considerably smaller in a red dwarf system. And this is again because there's not as much visible and near infrared light. So when you look at the efficiency of silicon solar panels and even other materials, it basically becomes highly inefficient and basically does not produce any power above 1100 nanometers. Okay, and this is when the midwave infrared basically starts. And you can see that while the radiation from Proxima Centauri peaks at around 850 or 900 nanometers, what we have to do is actually integrate the curves and show where the overlap is, okay? So for Proxima b, you might have something around 20% or 30% of the radiation is going to fall into the area that can get efficiently absorbed by solar panels. And with the sun, this is going to look more like 50%, okay? Now, we do have some materials that can absorb midwave infrared in the shorter wavelengths. However, these require really exotic materials like you can see here with indium, gallium, and arsenic. And these are not nearly as abundant as silicon, which you can find on pretty much every asteroid. Now, we also have a few other materials like quantum dot technology, but this uses lead, which is also very rare. And you can see it also only has a very narrow bandwidth of around 1100 nanometers. Now, like I said before, when you start talking about super cool red dwarfs that are going to last tens of trillions of years, they're going to be around 2000 Kelvin or just above there. So almost none of the radiation will fall into the visible spectrum. And this means that solar panels and of course photosynthesis are going to be completely useless. So if we consider a super cool red dwarf like something like TRAPPIST-1 or much cooler than that, you can see that the photosynthesis range and even the robo-habitable range using solar panels may actually fall within the area where liquid water will not exist anymore. Now, of course, this is assuming that we're going to be using silicon solar panels, but we do have a few other options in the distant future. First of all, we can use thermal electric generators. Okay, so for this, you basically just have a temperature differential, and then you use semiconductors to turn that temperature differential into electricity. Okay, and we actually already do this today in the form of radioisotope thermoelectric generators. So what we do here is we'll have plutonium, which is producing heat on one side of the TEG, and on the other side we have radiators that are cooling off by radiating their energy into space. And in between you'll have an energy differential and a heat differential, which is what's going to be able to produce power. So in a red dwarf system, you could just have a large absorber and use a material like water or some sort of dark material that can absorb infrared radiation. And on the other side, you could have a bunch of radiators, and in between, this is where you would put your semiconductors. Now, it usually requires relatively exotic materials for that semiconductor, but again, you can use planets and you can mine on planets to get these materials. And then also you can use cheaper materials like silicon if those materials aren't available. So with that being said, that does slightly expand this robo-habitable zone where advanced humans can exist and thrive, even in these super cool red dwarf systems. And of course, in the distant future, we actually won't need stars and solar power at all, and we could just use something like fusion and just getting hydrogen from water and things like this. So we conclude that it is possible for us to survive around these dim red dwarfs trillions of years from now, given very advanced technology. But I think I'll save the rest of that discussion for another video. Now I'd like to discuss the habitability in terms of life as we know it today. Now, habitability can be defined in many different ways, and people have all these sorts of different zones that they use to sort of describe potential habitability. Okay, but what most people really mean when they define habitability, they basically mean everything that's needed to form life, or for example, if we could just dump organisms into an ocean on a certain planet and they would be able to thrive and grow exponentially. So the best definition for this that I think is basically a planet that has surface water and an atmosphere and also enough visible light for photosynthesis. Now, the main challenges when it comes to actually having a habitable solar system are number one, the X-ray radiation, two, the stellar flares, and three, tidal locking. And these are all things that people talk about when they mention the habitability of red dwarf solar systems. Now, the first issue that comes up is the very high levels of X-ray radiation around these stars. And a lot of this is generated because of the magnetic activity associated with a smaller mass. Okay, so you can see here when it comes to the overall luminosity and how visible they are in the sky, you can see that Alpha Centauri, which is a binary star system with a G and K type star, which is much larger, and you can see Proxima Centauri, which is a red dwarf, is very dim. Now, when it comes to their X-ray luminosity, it actually comes out to around the same. So despite Proxima Centauri being very small and having a very low overall luminosity, it actually produces a similar amount of X-rays as does the Sun or other G-type stars. So because the habitable zone is much tighter around a red dwarf, the irradiance of this X-rays is going to be much stronger even though the overall luminosity is the same. So for Proxima b, which is a planet that's in the habitable zone of Proxima Centauri, our nearest star, that's a red dwarf, it orbits around 0.05 astronomical units compared to 1 astronomical unit for the Earth. So if you use the inverse square law, you can see that it's around 400 times the X-ray irradiance that the Earth gets. And when you assume no shielding, this works out to around 45,000 rems per year, which is very extreme and completely inhospitable for life as we know it today. So as you can see here, this is how they get to the number of 400 times the X-ray irradiance around a red dwarf. And you can see as the star gets larger, that's going to go down significantly. However, they are much more abundant, and because of their lower luminosity, they're burning fuel slower, and they're going to last 100 billion years to several trillion years. Now, the X-ray radiation actually isn't as big as a problem as you might think. So, if you've ever been to a dentist office or a doctor's office, they'll usually just put a simple little shield over your parts of your body to prevent you from getting cancer from the X-ray. And they're able to do this because low energy X-rays are stopped very easily with basic shielding. So as you can see in this chart, if you start out with 45,000 rems per year, which is very extreme, a simple 10 centimeter layer of water brings us down to 500 rems per year, and 50 centimeters of water, which is what most life forms in a planet's ocean are going to be having, okay, in the top layers of the ocean, the radiation becomes completely negligible. Now, same thing for a human habitat. If you had glass to protect your solar panels, you just need to make it considerably thick. And then for a human habitat, you could just use something like 1 centimeter of steel, and the radiation is going to be completely negligible. Okay? So you're not going to see terrestrial life, but it's not going to be an impediment to life in an ocean, for example. Now, the main problem with the X-rays is that they're going to start removing the outer atmosphere, and over time they can remove a lot of a planet's atmosphere, especially when you combine this with stellar flares. So most red dwarfs, or at least a significant number of them, are flare stars. Okay, so they're much more active compared to the sun, and they have massive mass ejections from the star, and they also have massive amounts of X-rays that come in these bursts. Now, we should mention that planets orbiting red dwarfs will still have a magnetic field that will somewhat protect them from this radiation and from the mass ejections in particular. So for Proxima b, it's tidally locked to its star, but since it's tidally locked, it's still going to be rotating once per orbit, which works out to around once per 9 days. Okay, so if you do the math like they did in this paper here, this works out to a magnetic field strength of around 0.3 or 30% compared to the Earth. So this is still going to provide some protection from solar flares, but the stellar flares are still going to be very serious. As you can see here in this paper, the stellar flares at Proxima Centauri are completely incomparable to what we see at the Earth. So in fact, in this one flare in 2016, they found that the star became 68 times brighter for over an hour. Okay, so that's an incredible amount of energy release. And you can imagine it's sort of like when you use a magnifying glass on ants, except it's probably even 5 or 10 times more powerful than that. And so you can see that over a course of an hour, you could have considerable amounts of an ocean that are going to get boiled off. And this could probably lead to some pretty severe runaway greenhouse effects, even within just an hour time frame. And now, these stellar flares only happen maybe a few times a year for a star like Proxima Centauri, but they're still very serious. So in this other study, they estimated that this would remove around 90% of a potential ozone atmosphere in an Earth-like planet. So the UV radiation will be very extreme, and of course the X-ray radiation was already extreme. So again, you're not going to see terrestrial life, but this is not necessarily going to affect life in the oceans, because life in the oceans will have the UV and X-ray radiation blocked by the upper layers of the water. Now, in this other study, they estimated how much of the atmosphere would be removed due to the radiation and the stellar flares. And they estimated that with no magnetic field, you would lose around 87 Earth atmospheres, which is very extreme. And when they did calculate using a magnetic field, it was much more reasonable, but it was still 3 Earth atmospheres per billion years. Now, for most planets, this will probably strip away the atmosphere very quickly. However, for a very significant ocean planet, the significant mass of volatiles in the ocean is going to be able to replenish the atmosphere. So you can see with the Earth's ocean is about 3 orders of magnitude greater than the Earth's atmosphere. Okay, so it's going to take a significant amount of time to fully remove the atmosphere, even if you're stripping away 3 Earth atmospheres every billion years. And planets also have other mechanisms that can replenish the atmosphere through geological processes, or for example, water trapped in the mantle coming back up to the surface, or things like this. Now, for the habitable zone of a solar system, this is not going to be as far out as the frost belt. Okay, so you're not going to have massive layers of the planet that are going to be water, like you see on Ceres, where basically the entire mantle is made of water, okay, or on gas giants where they have significant layers of water. So it's not going to be so extreme that you're going to be guaranteed to have an atmosphere on these planets, okay, but it's also going to help out when you have super Earths or maybe like sub-Neptune planets that are maybe something like twice the mass of Earth, because these planets are going to be able to hold on to their atmosphere through gravity much better than an Earth-sized planet would. It's also important to mention that most of the planets that we observe around these small red dwarfs are actually Earth-sized or super Earth-sized. So you're not going to see a lot of these Neptune-sized planets, okay? And we see that with systems like TRAPPIST-1, for example. Okay, moving on to another study about stellar flares. So this study also suggests that for Proxima Centauri b, that the escape rates will be 2 orders of magnitude higher than what we see on Earth if it's unmagnetized. Now, if it does have a magnetic field, they said that it would be significantly better off. I should mention here also that the magnetic fields are expected to last a similar amount of time just from their internal heat, since you pretty much require a liquid metal or moving metals in the core to have a magnetic field. Okay, so these are expected to last for billions of years. They're not expected to last on the time frame of trillions of years, when we'd be talking about where red dwarfs are the only stars left and we need to use them for our survival. So just keep that in mind as we talk about this. Now, this is a conflicting area of argument. As you can see here, this paper, basically they simulated just putting the Earth into the Centauri B system. Okay, so slightly larger rotation rate and larger magnetic field. And they still suggested that the Earth atmosphere would be degraded and get removed over time if we just plopped it into the Alpha Proxima Centauri system. Now, as we're starting to observe exoplanets directly through things like the James Webb Space Telescope, we can start to see evidence that they actually don't have atmospheres. So we have this system called TRAPPIST-1 that has something like 7 Earth-sized planets, and a lot of these are within the habitable zone of that star. Now, the first two, TRAPPIST-1 B and C, are outside of the habitable zone. They're actually too close to the star to have liquid water. However, we could expect them to have something like a Venus atmosphere, okay, if we had a situation where the solar flares were not removing the atmospheres completely. Okay, but the early evidence is showing that these appear to be sort of a bare rock type planet, sort of like Mercury, okay, even though they're closer to the size of Earth and Venus. Okay, so this is suggesting some serious evidence that these atmospheres are going to be stripped away in red dwarf systems. And I should also mention that TRAPPIST-1 is also a very dim red dwarf, so we can expect it to be more active and have more thermal energy than visible energy, like we discussed before. So in conclusion, when it comes to atmospheres, we can expect them to be much rarer around red dwarfs in the habitable zone compared to a star like the Sun. That's a G-type star. Okay, however, you can imagine that under the right conditions, say given a regenerating atmosphere or a very large planet that could hold on to its atmosphere, or again, a very strong rotation, and that could provide a very good magnetic field, especially in these larger, more luminous red dwarfs where you could orbit from further away and the tidal effects would not be as strong, so you wouldn't necessarily get tidal locking. Okay, so this is going to increase the power of your magnetic field, making it more possible to hold on to your atmosphere. Okay, so I think the key question, the most important detail, is whether or not the planet is going to have an atmosphere when it comes to life as we know it today. But we also have this secondary thing to talk about, which is tidal locking. Okay, so a lot of people think this will also be a reason that these planets will not be habitable. So tidal locking is when you're in a very strong gravitational field and you're orbiting very close to the object, something like Jupiter or the Sun, and you'll end up with these tidal effects that change the rotation of the planet. Okay, so Mercury is in a 3:2 ratio resonant orbit around the Sun, okay? So it's only rotating around about 3 times compared to two full orbits of the Sun or something like that. Okay, and then you could also have planets, or like for example the moons of Jupiter, or actually the moon of Earth, that are tidally locked, and so they're always pointing around the object as they rotate, and they have the same rotation speed as their orbit period. Okay, so like I said before, these tidally locked planets are still going to have some rotation. They're just going to be rotating slower than they would originally. Okay, so they're going to still have some magnetic field. So just keep that in mind. Okay, so something that people worry about is having these ice caps that would lock in the atmosphere and potentially freeze the atmosphere and freeze all the liquid water on these planets, making life impossible. However, researchers have found that if you just have a surface ocean that doesn't even need to be as large as Earth, that it can transfer all the heat necessary to prevent the atmosphere from freezing, or even the entire ocean from freezing on the far side of the planet. So this study suggested that the temperatures would not even fall below 240 Kelvin, so that's only minus 30 Celsius. So that's actually pretty similar to what we see on Earth at the North and South Poles. Other papers have suggested that you actually don't even need oceans. You could just have an atmosphere to do this heat transfer successfully. Okay, so this paper suggests that something like 1% to 10% of Earth's atmosphere will be sufficient to transfer the heat to the other side and prevent the atmosphere from freezing. Okay, however, I should note here that having a freezing atmosphere could actually be very useful in the long term when it comes to robo-habitability with advanced humans. So if you have a frozen atmosphere and it freezes all the volatile chemicals like H2O and CO2, these wouldn't be available for life, kind of like how it is on Mars, okay? Now, obviously this wouldn't support life as we know it. However, if we had a situation like this in the distant future, we would still have all those chemicals available. They wouldn't be stripped away, and even with no atmosphere, you could have everything that you need for life, given a situation where you could build solar panels or thermal generators on the tidally locked side with robots, and then you could also have the volatile chemicals to support humans and support everything that you need for your civilization. Okay, now other papers have suggested that for these tidally locked planets, there's going to be so much tidal heating that they could turn into a Venus situation, and the heating would be so extreme that it would cause a runaway greenhouse effect. Okay? Now, this is a valid point, but again, this would probably just move the habitable zone further out. It wouldn't necessarily remove the habitable zone completely. Because again, you'd get to a point where the tidal heating would be less, and also the radiation from the star would be less. And so, once again, you could have liquid water there. When it comes to tidally locked planets, I really don't view these as an impediment for life. And I think it's actually sort of binary thing where it'll either help the current form of life that we know today and be less useful in the future, or it'll become impossible for the current life today, but it will help out for very advanced humans and very advanced life forms in the distant future, trillions of years from now, when the volatiles will be locked. Or it could be something in the middle, where you can see here where you have a terminator region that will be habitable, and then you'll also have the locked off ice on the far side of the planet. So, in conclusion, when it comes to tidal locking, you might have some really crazy weather events going on. You could have entire parts of the planet that are total deserts, or constant torrential rainfall, or just completely locked off in icebergs and things like this, ice sheets. But regardless of what it actually looks like, it's sort of a win-win situation for either life as we know it today or life in the distant future. Okay guys, so in conclusion, I think that red dwarfs have really gotten a bad rap in the media these days, and they can actually be really useful for us in the future. So when it comes to habitability and life as we know it today, I think it'll be much rarer, but I think it's totally probable for the larger and less active red dwarfs that are higher temperatures. For the lower temperature red dwarfs like TRAPPIST-1 or even darker, I really don't see life forming there naturally, just because of the photosynthesis problem and the more active nature of these stars. However, I think in the very distant future, trillions of years from now, the thermal energy of these stars will be very important to harness, and they may be our only hope for survival. So with that being said, guys, I hope you learned something today, and I hope you liked the video. Make sure to like and subscribe, and let me know what you think in the comments about red dwarfs. And with that being said, thanks for watching, and have a great day.